Catalan, and this is my presentation. The purpose of this experiment is to observe the motion of an object moving at the same speed without changing direction. In other words, this object is moving at a constant velocity, which means that there is no acceleration. We are also comparing data that has been extracted experimentally and predicted computationally. Newton's first two laws will be used in this experiment. Newton's first law states that an object at rest or in motion will remain at rest or in motion unless an external force acts upon it. In this experiment, we are assuming that the object will be moving at constant velocity, which means that there will be no external force applied to it as an assumption. Newton's second law relates to net interaction between the system and the surroundings to the observed motion of the system, which can be seen as a change in momentum. Momentum is how easy or how difficult it is to change the motion of an object. Newton's second law is more commonly seen as F equals ma. A second form can be found by using the momentum equation. By using this second equation, or second form, and rearranging it and expanding it, you get the momentum update formula. By dividing the momentum update formula by mass, you get the velocity update formula. In this experiment, we are assuming that our object is moving at constant velocity, which means that there is no acceleration, which means that there is no net force. By substituting 0 for the net force in the velocity update formula, we get the final velocity is equal to the initial velocity. The position update formula can be found by getting the velocity equation, expanding it, and rearranging it. This is used for computational prediction. In reality, forces will always be present, such as gravitational force and normal force. And in motion, you get two more: air resistance or drag, and friction. This means that while we assume or predict that our object will be moving at constant velocity, in reality it will not be, because it will be experiencing some form of friction and some form of air resistance. This is the object moving in motion. As seen in the video, the system is a glue stick and the surrounding is a counter on top of it. Since Earth has some forces acting upon the glue stick, such as gravity, it is also seen as a surrounding. Normally, the initial position is the origin 0, 0, 0, but Tracker gives 5.991 e to the negative fourth as the initial position, so we are using that instead. The initial velocity can be found by using the first two frames in Tracker, which gives the first two data points. By subtracting the two position vectors and dividing by the change in time, we get the initial velocity 0.127 meters per second. In the first half of the coding, we have this. This is the position vector described beforehand, and this is the velocity vector, initial velocity vector described beforehand. The y and z component is given as 0 because we are only looking at the x component. Delta t is given as 1 over 30 because the video is filmed in 30 frames per second, so it is given as 1 over 30 or 0.033 repeating. This is the second half. In this loop, we have time being less than or equal to 2.133 because this is the final timestamp for how long the video went on. The net force is given as 0, 0, 0 because we are assuming this. This right here is the velocity update formula, and this portion right here is the position update formula. With these two, we are able to use Newton's second law. This is the computation in progress. As you can see, it gives us a position time graph with constant velocity. Here we have the computational data that we just saw with the experimental data that we got from Tracker. Normally, the computational data is above the experimental because in reality, no object will continue moving in constant velocity. It will experience some form of frictional or air resistance. However, in this case, our experimental was above for some reason. This could have happened because the points per frame was chosen poorly when calibrating Tracker, or the counter could have been at a slight angle. However, this is not very likely because in the end the glue stick did end up slowing down and stopping, which is what the second point is saying. What if the orientation of the axis were flipped? Time normally progresses going forward. It does not move backwards logically, but if it was placed in the negative x direction, it would appear as a reflection across the y-axis, the graph. If position was increasing in the negative y direction, it would also appear as a reflection, but across the x-axis. Is it possible to say how many forces add up to a net force of 0 computationally speaking? In theory, you could say 2 for air resistance and friction, but in reality you can't because other forces could be acting upon it, And air resistance has more implications because of the air molecules. It's composed of different ratios of nitrogen, oxygen, and other things. Also, temperature could increase how fast the molecules are moving, which may increase or decrease the force applied. And friction is used with the materials. The glue stick was composed of paper and plastic, and it was also not a perfect shape, which could also alter how much force was applied to it. So, no.